All right, I'm going to really quickly go through the wave mechanical model of the atom and then show you about how to look at atomic orbitals and electron configurations. Now, I'm going to try to be as succinct as I can in describing the evidence for this model, but this is really the modern model. This is the model that we use now for understanding how electrons are arranged around the atom. And it's based on this idea that, like light, electrons have both wave and particle-like properties. And so this helps us explain why electrons exist at these distinct energy levels that Bohr was representing with rings. Now, there was a scientist in the 1920s named Schrödinger, and what he did is he solved some really complex equations to give us a better understanding of how electrons are arranged around the nucleus. And so the equations and the solutions are complex, and my goal here is to simplify them, and we're going to look at them in a conceptual way. Now, they give an account of energy levels that's similar to Bohr's model, that there are distinct energy levels that electrons exist around the nucleus. But what he did, or what Schrödinger's model does, is it models the location of electrons based on three-dimensional orbitals. And the orbitals don't tell us exactly where electrons are, but tell us where they likely are located around the nucleus in three-dimensional space. So based on these, the solutions to these equations, the orbitals have different shapes and energy levels. And the two shapes that we're going to be looking at are s orbitals, which have a spherical shape, and p orbitals, which we say have a dumbbell shape. Now, a sphere, you can orient any way around the x, y, and z axes in 3 dimensions. It's going to look the same. There's only one s orbital per energy level. But the dumbbell, the p orbitals, you can orient in 3 different orientations on the x, y, and z axis. So there are going to be 3 p orbitals per energy level. Now, this probably doesn't make sense yet, but just bear with me as we go through this. So, just like Bohr, Schrödinger's equations predict that electrons exist at distinct energy levels, and we're going to label these energy levels with numbers. But Bohr proposed that electrons orbit around the nucleus kind of like planets around the sun. Now, did he actually think that's how it goes? No, but he didn't have a better explanation. The Schrödinger wave equations gave us orbitals. Now, these are, again, the 3-dimensional areas around the nucleus where finding an electron is highly probable. Can we pinpoint where an electron is around the nucleus? No, but we can tell you where you're likely to find it. And so we do this using 2 of the solutions to the Schrödinger wave equation. One is called the principal quantum number. What this does is it tells us the energy level of the electron. And so the first energy level is just 1. The second energy level we just label 2, and so on. So because electrons exist at distinct energy levels, in the ground state, we're going to have the electrons occupying the lowest energy levels first. There's also something called the angular momentum quantum number. Now, these sound like big words, but basically what this does is it tells us the shape of the orbital. There are 4 different orbital shapes that we know of: S, P, D, and F. We're going to be focusing specifically on S and P orbitals. Again, S orbitals are spheres, P orbitals have a dumbbell shape. So when we're describing the electron configuration, or how electrons fill the orbitals, we label the orbitals with the principal quantum number, so that's going to be like 1, 2, 3, or 4, or so on, and the orbital shape. So for us, it's going to be either S or P. So for example, the S orbital in the first energy level is just called 1s. A P orbital in the second energy level is just called 2p. Now, there are 2 other, There are 2 other numbers that denote electron location and spin that we're not going to go over, but what you need to know is that electrons have opposite spins in the same orbital, and we represent that by having arrows pointing in opposite directions, but you'll see that in just a minute. Now, because all things in the universe tend towards the lowest energy state possible, electrons are going to fill the lower energy orbitals first before they go to higher energy orbitals. So here's what you're going to be doing. You're going to be doing something called orbital filling or orbital filling diagrams. Now, we're going to draw diagrams to help us understand which orbitals are occupied by electrons. So it tells us how are the electrons arranged in an atom. Orbitals are going to be represented by horizontal lines, and they're going to be labeled. And we're going to start with the lowest energy orbital, which is 1s, and we're going to move upward in energy until there are no more electrons to fill. Each orbital can hold 2 electrons. And each electron has opposite spin, and we're going to indicate electrons by arrows. The opposite spin is they're going to be pointing in opposite directions. We're going to be following 3 rules when we do this orbital filling. One is that an electron has to occupy the lowest energy orbital that can receive it. And the other really important one is called Hund's rule. Orbitals of equal energy are occupied by 1 electron before a second electron is assigned to that orbital. Now, this probably does not make any sense to you at the moment, but I'm going to show you how this works. Okay, so I'm going to try to keep this chart on the screen while we're doing this. We just have to do a couple of examples, and I think you're going to catch on. So what I'm going to do is I'm going to do the orbital filling diagram for, let's do fluorine. Now, fluorine on the periodic table is right here. Fluorine has an atomic number of 9, which means that it has 9 electrons. What we're going to do is we're going to follow the 2 rules that I highlighted to fill the orbitals for fluorine. So the first rule, an electron occupies the lowest energy orbital that can receive it. Well, we can use this chart to see that the lowest energy orbital is the first orbital on the bottom because energy increases as we go up. So the first energy that can receive one of fluorine's electrons is 1s. So what I'm going to do is I'm going to draw a horizontal line and I'm going to label it 1s. Now, each orbital can accommodate 2 electrons. So I know that the 1s orbital can hold 2 electrons. So we're going to fill the 1s orbital with 2 electrons that we represent with arrows, and they're pointing up and down to represent the opposite spin. So now that that's full, we've satisfied rule number 1, an electron occupies the lowest energy orbital that can receive it. So then we're going to move up to the next lowest energy, which is 2s. Now, here's what I'm going to say. Whenever you enter a new energy level, we're going to draw representations for all orbitals on that energy level. Okay? So once I go to 2, I'm going to draw 2s and the 2p's. Okay, so 2s is lower than 2p. We have 9 electrons to assign. We've assigned 2 of them. So we can assign 2 electrons to 2s. So now we've assigned 4 electrons. We have 9 total, so we have to assign 5 more. 2s is full, so we're going to move up to 2p. Now, each of the 2p's, according to this chart, are equal energy. And so now we have to look at Hund's rule. Orbitals of equal energy need to get 1 electron before they get a second electron. So when we're assigning these last 5 electrons, each one of these can hold 2 electrons. But what we need to do is give one to each first before they can get a second. And this is where I would stop because I've assigned 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So this would be the orbital filling diagram for fluorine. Okay, let's do another example. let's do phosphorus. Phosphorus is number 15. That means it has 15 electrons. Okay, so we're just going to follow these 3 rules. An electron has to occupy the lowest energy orbital that can receive it. So the lowest energy orbital, according to this chart, is 1s. And this will get 2 electrons. So we've assigned 2 of the 15 electrons. The next the next lowest is 2s. So we're going to draw out the whole second energy level. 2s and 2p. Now, 2s is a lower energy than 2p, so we need to fully occupy 2s with 2 electrons before the 3 2p orbitals are going to get occupied. So we've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've done 10 of the 15 electrons. So then we have to keep going. So after 2p is 3s. Now, because I'm moving up to 3, I'm going to draw out all of the orbitals that we're going to be talking about in the 3rd energy level. Okay? So we've assigned 10 electrons. So 3s is lower than 3p, so we're going to do 11, 12. And we have 3 more to assign, and we have 3 3p orbitals. So this is where it's important to remember Hund's rule. Each p orbital gets 1 electron before a second is assigned. So the last 3 electrons go 1 each into each p orbital. Now, here's a little trick. So you don't need to do this on your paper. I'm just doing this to highlight this phenomenon. So these are the electrons in the 1st energy level. These are the electrons in the 2nd energy level. Notice how it's 1. These are both in energy level 2. And these are both in energy level 3. If you look at, for phosphorus, this is really small, so I want to make sure. In the upper right-hand corner of your periodic table, it says the numbers 2, 8, and 5. If you count the number of electrons in the 1st energy level, it's 2. If you count the number of electrons in your 2nd energy level, I gotta focus again, sorry about that. If you count the number of electrons in your 1st energy level, it's 2. If you count the number of electrons in the 2nd energy level, it's 2, 4, 6, 8. And the 3rd energy level is 1, 2, 3, 4, 5. So when I tell you all of the information you need is on the periodic table, I'm not, it's no lie. Everything you need is right here. It tells you the answers. And so that's a really good way of checking your orbital filling diagram. That's where I'm going to stop. We're going to do a bunch of examples in class, but this will be here if you need it.